Hi, NA Physics. It's Mr. Neff. Today we're going to talk sound intensity. Before we do, what do you get when you cross a cement mixer and a chicken? Watch to the end of the video and I'll tell you. So when I say sound intensity, I mean how loud a sound is going to be. But not just that, I mean how much energy is actually going to be going into your ear, and you're going to interpret that as the loudness. Now, you have to remember that sound is a longitudinal wave, and so it consists of high pressure areas and low pressure areas, and higher pressure areas and lower pressure areas. And so you can see in this tube of sound, I've got areas where the pressure is high, and I have areas where the pressure is low. High here, low here. High here, low here. When I say high, I really should be saying higher. And when I say low, I should be saying lower, because we're saying that we're higher than atmospheric pressure, we're lower than atmospheric pressure. Now, if I wanted to show you some air that didn't have any sound going through it, I would draw something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 air molecules in there. There are way more than 10 air molecules in a space that big, but you get the idea. In the box adjacent, I'll draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same amount. Bear with me here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All those boxes have 10 molecules in there. There's no fluctuation, no difference in pressure from one area to the next. And so we say that that's a picture of silence. And so if I wanted to show you a graph of that, like say I quote unquote played the silence into the microphone, the graph of that would just look like so. It would just be a nice steady 1 atmosphere of pressure. Now, if I had a really soft sound being played, let's say it's a sound that's just barely audible to a human. Well, I might have a tiny little difference between one box and the next. And so maybe I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, undo that last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, undo that last one too. Now, you can't really see it by looking, but you counted along with me, and so you know that there really is a difference box to box. There is 11, and then there is 9. And as those disturbances move across the microphone, you'd see a fluctuation in the pressure on the graph. You would see that at this spot it would be at 11. I'm trying to draw it right underneath that box. And then at this spot it would be 9. And 11, or whatever amount of pressure corresponds with 11, and then 9. And then 11, 9, 11, 9. And I've exaggerated that so you can see something, but we're looking at a wave, something like that. Now, I said that that was going to be the softest sound that a person could possibly hear. Let me zoom in. The softest sound that a person can hear we call the threshold of hearing, and we'll talk more about that in a second. But I will say that it is generally considered to be plus or minus 3 billionths of an atmosphere will make the eardrum vibrate violently enough with enough amplitude that a signal will be sent to the brain. If this fluctuation were a little more subtle, maybe the fluctuation is only that large, well, there may be animals that could hear that, and that can still vibrate your eardrum, but it's not going to make a signal go to your brain. It's underneath the threshold of hearing. There's not enough work being done on your eardrum to make a signal go to your brain. Now, as the sound gets louder, you can imagine what's going to happen. As the sound gets louder, the difference between high pressure and low pressure is going to be more significant. And so I'm going to have maybe, instead of 11, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and only 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 1, 2, 3, 4, 5. And now you can see that that's going to give you a wave that's way higher when it's high and way lower when it's low. Higher and lower than it was before. And so you can see that whenever these disturbances move onto your eardrum, it's going to vibrate with a lot higher amplitude, and you're going to say, oh, that is louder. And so a louder sound is going to be a higher amplitude sound, and that makes perfect sense because more work was done on that air, and so more work is done on your eardrum, and you can see the amount of work by the amplitude. Now, of course, there's a limit to all of this, isn't there? Because I can only go so far. How much difference can I possibly make? Well, 1 atmosphere. I could have all the molecules, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and none. And then all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and none. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Notice something here. There is twice as much air in the same volume as there was when we had no sound. And so that's up to a pressure of 2 atmospheres. And there is nothing in this spot. It's a total vacuum, and that is 0 atmospheres. And so this represents the loudest possible sound in air because this is the biggest difference between high pressure and low pressure that you could possibly get. And so this sound is going to go all the way up here and all the way down to the axis because that's where 0 pressure is. And so here is our loudest possible sound. So anytime you want to see the volume, anytime you want to see the intensity, you look at the amplitude, and we've known that for a while. Now, loudness, as I said a few times, it's a subjective measure of the amplitude. It's going to vary a little bit person to person to person. Loudness is subjective, but an objective measure is called sound intensity, and it is a measure of how much energy is going through an area in an amount of time. We like to say that it's the concentration of sound energy, and I always like to say it's the harmfulness of sound energy too. So we're going to say that the amount of energy transported per second is the power, and we remember that from units ago. So sound intensity is that power divided by the area. And so anytime you want to figure out the intensity, you're going to take the power and divide by the area. That's something that you'd want to know going into an exam. Take this speaker, for instance, and say this speaker is putting out sound in these rectangular areas. Well, if the amount of energy that a speaker is going to put out every second is going to be the same. And so here, say that it took the same amount of time to make this one, and earlier it made this one in the same amount of time. Well, here you can see that the sound energy is spread out over a small area like that, and so it's still going to be fairly intense, a lot of energy per unit of area. Versus here, the intensity is going to be smaller because the energy is spread out over a larger area. I like to think of it as spreading peanut butter on bread. If you don't spread it out very far, it's kind of intense where it is. It's thick where it is. But if you spread it out really far, then it's thin or not very intense where it is. Consequently, you'd see that it was less intense and less volume whenever it hits your eardrum. Now, in our class, we'll only deal with sound that's traveling out uniformly in all directions. And so our area is going to be the area of a sphere. And so you're going to see very, very often that the area of a sphere, surface area of a sphere, 4 pi r squared is going to show up in that denominator a lot. Here's a nice example. So here we have a sound source that can output sound in all directions. The wave fronts are going to take the form of spheres. And so now you can see a wavefront B that's farther away from the source because it was produced first and it's had more time to leave. And then you're going to see wavefront A, and it was produced second and it had had less time to get away from the source. Now, they have 3 little patches marked off on the wavefronts. That kind of makes sense because they might represent the area of your eardrum. Even though they drew them squares, they still would represent the area that the energy is passing through. And so it says that we have these, the sound source is producing 2.3 watts or 2.3 joules every second of sound power, and we have the radii as 0.6 and 0.8 of those two. And it says determine the sound intensity in each one of the 3 patches. Well, for part A, the patch 1, its intensity is going to be the power divided by its area. And so the power is 2.3 watts, and the area is going to be 4 pi r squared, and the r is going to be 0.6. Don't forget to square that, 0.6 meters. If you go ahead and run those numbers through, you will get 0.51 watts per square meter. Now, that's a representative number of everywhere on this sphere. They're only showing the cross section of it there, but every spot on that sphere. If you mark off a square meter on that sphere, you'll be marking off a place that has 0.51 joules per second going through it. If you mark off a smaller amount, then it's going to be only a fraction of 0.51 watts or joules per second. Both patch 1 and patch 2 are on that sphere. And so right now, maybe I don't know how big they are relative to each other, but I know that the intensity is an intensity of a spot. And so whether you talk about this spot on the sphere or the spot at patch 1 or you talk about the spot at patch 2, they all have that same intensity. So that number was going to be good for patch 1, but it's also going to be good for patch 2. Not patch 3 though. For patch 3, it's farther away. And so the peanut butter is spread out thinner out there. And so when I do 2.3 watts and I divide by this area, I'm going to get a smaller number because I'm spread out over a much larger area. And if I go ahead and run those numbers, I get 0.29 watts per square meter. It's less intense out there, and you know that from your experience. The farther away from the source you are, the quieter it's going to be. Now in part B, they say the sound power that passes through each of the patches is the same, 1.8 times 10 to the minus 3 watts. Find the area of each patch. Well, now if I'm going to say if the intensity is power divided by area, that means the area is going to be the power divided by the intensity. And so I'll take that power that they gave me, 1.8 times 10 to the minus 3 watts, and I'll divide by that intensity, 0.51. So a good way to think of this is saying, all right, well, if the power that you want is 1.8 times 10 to the minus 3, and you are at a spot where it is spread out to a thickness of 0.51 watts per square meter, then how many square meters do you need? And so you'll see that this area 1 is going to be 3.5 times 10 to the minus 3 square meters. And if I did the same thing for number 2, well, all the numbers are the same. And so that area is going to be good for number 1, and it's going to be good for number 2. Now, if I divided by a smaller intensity, 0.29 watts per square meter, well, of course, this answer is going to have to be bigger. A math kid will say, well, you're dividing by a smaller number, so the answer is bigger. Of course, they're right. And a physics kid would say, well, if it's less intense farther away, then the area is going to have to be bigger to catch the same amount of energy. And if you run the numbers, you'll see that you're totally right on that. 6.3 times 10 to the minus 3 square meters on that area. Just to give you some perspective on the intensities, that intensity of the threshold of hearing is taken as 1 times 10 to the minus 12 watts per square meter. And that's a number that you'd want to know going into an exam. Another number that's helpful in the problems is the threshold of pain, and that's generally taken to be 1 watt per square meter. Hey, just to wrap it up, what do you get when you cross the cement mixer and the chicken? You get a bricklayer,